Hi, my name's John Perham from the School of Mathematics and Statistics at the University of New South Wales. This is an extended version of the talk I will be giving entitled Integration of Computer Algebra Systems into Freshman Mathematics Instruction at the Computer-Based Mathematics Summit in London this week or next week. So let's get started. So here's an executive summary. I will start by telling how I got involved in computer-enhanced education mathematics instruction some 15 years ago, and then will then review current freshman mathematics instruction against the principles of competence-based curriculum design and show that the traditional competences are the ability to carry out technical calculations under time pressure without access to any of the resources available in a realistic working environment. And I'll then outline an alternative in which students learn all the technical content by analysing a number of applications, with this content structured as interoperable, customisable, symbolic, numerical and graphical code fragments. And based on my experiences teaching courses in dynamical systems and analytical mechanics, I will demonstrate that this alternative applies a shift in effort from delivery to preparation and evaluation. And I will finish by discussing the costs, benefits and impediments to this program and how the latter might be overcome. So start with the background to the summit. Start by this. Well, if computers were invented by mathematicians and computer algebra was one of the first applications of artificial intelligence, why are computers used less in mathematics education than in almost any other field of study? And this question was recently asked by Conrad Wolfram, who argued that current mathematics instruction focuses on technical calculations. Because these can be largely automated using computer algebra systems like Mathematica or Maple, he argued that the emphasis should be shifted to using mathematics to solve problems which can be formulated mathematically. Essentially, he's arguing for a shift in teaching philosophy from pure to applied mathematics, facilitated by integrating mathematical software. Well, what are my experiences? Well, I've been investigating ways of doing this for about 15 years now, and will try to communicate some of my experiences and results. Back then, I was teaching a course in dynamical systems at the now University of Southern Denmark, using the traditional methodology of lectures, tutorials and a written examination. And I began to use Mathematica to generate solutions to the written examination problems. The following year I devised another set of problems and found that the notebook with the previous year's solutions could be rapidly customized to solve the new ones. The fact that we could write a piece of software which could pass a written examination caused me to question what we've been doing all along and to think that there might be a better way. So, and there is a better way. So let's go on to what the next topic, which is competence-based curriculum design. This is a concept which has been largely pioneered by medical educators, but it applies to everything. So in designing a curriculum, such as freshman mathematics, one should answer the following three questions in order. So question one is, what competences do we wish the students of the course to acquire? Or you might say, why are we teaching this course? And question two, is how do we evaluate that they have acquired these competences? And question number three is, what do we teach? Let's go to the competences. Anyone who's taught mathematics will know that in the traditional curriculum, the questions are answered in the reverse order. Firstly, a textbook or compendium is chosen whose table of contents defines the curriculum. Then a method of evaluation is chosen, which is usually a written examination, possibly combined with tests, and this being the cheapest form of evaluation. And then the teacher flounders around to define the competences which are in fact the ability to pass the written examination. So let's now try to answer the questions and in the suggested order and see what emerges. Well, yes, here we go. Since most students of freshman mathematics are studying engineering or science, the purpose must be to equip these students with knowledge to support their future studies and practice. And this knowledge includes, let's fix that, one, all the standard technical knowledge of the traditional curriculum. Secondly, the ability to formulate quantitative problems from the real world as mathematical problems. And 3, the ability to solve them using the technical knowledge. And finally, 4, the ability to evaluate the solution in the light of the application. All in an environment where they have access to all the support which would be available in the real world. In other words, access to the internet, computer algebra systems, technical document preparation. Well, evaluation of competences. Well, the 4 competences above fall into 2 categories, one of mathematical knowledge and meta-knowledge, the latter being knowledge about how to formulate and solve problems using mathematics. This latter form of knowledge could also be described as problem-solving skills. So let's look at what we do at the moment, the traditional written examination. Well, the technical content of the freshman curriculum is well defined and probably universal. Students learn about a number of mathematical objects such as the numbers, functions, equations, vectors, matrices, determinants, differential equations, probability, and so on, as well as operations on them. They learn how to internalize this knowledge by repetition in tutorials, the success of this process being assessed in written tests of various kinds. For example, the process of row reduction in the solution of linear equations, the evaluation of determinants, the calculation of eigenvectors, and the inversion of matrices is largely arithmetic, the real knowledge being the interpretation of the results in terms of the original problem. And this may be rendered impossible due to a simple arithmetic or transcription error. And since the process is an algorithm, students would learn more linear algebra and problem solving giving rise to it by building a software tool which can be customized to different applications. The written examination is totally unsuited for evaluating meta-knowledge, largely because of the time element. Likewise, is not suited to testing knowledge if a computer algebra system is integrated, because it's possible to build a library of customizable solutions to all the standard problems. So that's what we do at the moment. So let's look at what we might do, what competence-based. So we need to evaluate the technical knowledge and the problem-solving skills. However, if students build a sequence of annotated tools for carrying out the various steps, they can concentrate on the interpretation. If they store these tools in their electronic toolbox, then this knowledge can be evaluated in an oral examination where the students are asked to show how to solve one of a set of random problems using their toolbox. The criticism of traditionalists of students using computer algebra systems as black boxes is met, since this methodology involves their learning how the black boxes work. Once they've done that, of course, they can use the black boxes. How about problem-solving skills? So, Professor John Sweller, an educational psychologist, has written a provocative article in which he compares problem-solving skills to the knowledge of chess grandmasters. We're going to have a quick look at that here. This is his article in the Notices of the American Mathematical Society, which you can download from their site. Let's go back. Anyway, citing work by Dutch psychologists in which they found the only significant difference between grandmasters and weekend players was the ability to reconstruct board positions from actual chess games, he concluded that chess grandmasters achieve their mastery by studying a large number of previous games so that they are able to recognize which tool in their arsenal will best deal with the current situation in the game. This is why they will always beat any number of weekend players. I found this argument convincing and believe that mathematical problem-solving skills are best learnt by studying worked examples and by solving problems, possibly by customizing and extending the solutions of existing problems to solving new ones. And to this end, I've placed videos of solutions to test and tutorial problems on my YouTube channel, Hypermath. Well, competences should be evaluated in a realistic environment in which students will use them. In my previous courses held at the Maersk Institute at the University of Southern Denmark, each student studied 3 large projects spread over the semester, handing in reports for each in the form of Mathematica notebooks at intervals of about a month. And they were able to obtain advice from a weekly meeting with a tutor who would also be involved in the evaluation process. So given the time frame, it is a requirement that all aspects of the solution are correct. When the course on analytical mechanics was taught and examined traditionally, the pass rate was about 2/3, 66%. And when I taught it using the new methodology, the pass rate did not change appreciably. However, of the students who completed the 3 projects and produced a toolbox, all passed, mostly with very high grades. And the constant workload was simply too much for the less serious students who just dropped out. So what do we teach? Well, let's start with the syllabus. Over the 12 years or so I've been working on this project, I've devised a small number of applications of mathematics, each of which motivates acquiring the standard collection of technical knowledge. Of this collection, the top topics most used by engineers and scientists are differential equations and 3-dimensional vector geometry. The first project concerns the frictionless vertical motion of a particle and motivates learning about linear functions, the solution of linear equation, the concept of integration, quadratic polynomials, solution of quadratic equations, differentiation of simple functions, and the fundamental theorem of the calculus. Subsequent projects taken from elementary physics motivate learning about differential equations, Taylor series, convergence of infinite series, the exponential function, the inverse function theorem, logarithms, the trigonometric functions, and complex numbers. Projects based on 3-dimensional geometry motivate the study of linear algebra, made more real because of the possibilities of visualization and animation. And these projects, and the order in which they are introduced, have been carefully chosen so that the technical content is introduced without redundancy or forward references. Thus, students learn all the current technical content of the freshman curriculum in response to a need to solve a problem. To illustrate how mathematical knowledge can be structured as reusable code fragments, we illustrate with some of the material from the first notebook, which will give some idea of how the learning material is constructed. So let's look at that. So the first bits of code involve the velocity of a particle projected upwards with velocity v0, subject to gravity but neglecting friction, which is a linear function of time, which we can establish using this. Now this is a Mathematica code fragment, and when I execute it, then what that effectively does is give a name, linfun, to the linear function, which is v0 minus g times t. And in this expression, t is called the variable and can be established as such using this. That's another piece of code. And if we want to visualize all this graphically, or that is, plot this function, we'll need to assign some parameters. So let's give the particle a upward vertical velocity of 20 meters per second and assign a value to the acceleration due to gravity using that. So these are what these do, if we execute them, is it temporally assigns values of the parameters so we can do that by this command here, which replaces in this temporary function the symbols v0 and g with their numerical values. And now we can, because that only contains the variable t, we can plot this function as a function of time as a thick red curve, and with the axes labels defined as such. And there you can see why this function is called a linear function. So it is a straight line, and it goes down. The velocity goes down and eventually becomes 0 when t is about 2. That means physically that the particle starts going upwards and then is slowed down by the gravitational acceleration, and eventually reaches its maximum height, and then it falls, and then thereafter the velocity is negative, which means that the particle is coming down. So the variable v, which represents the velocity of this particle at some subsequent time t, satisfies a linear equation whose left-hand side can be established using that. So, so we subtract from the velocity v the linear function, and I've been using the convention that all equations have the form left-hand side equals 0. And that the reason why that's an advantage is that we can multiply them by non-zero scalars and so on. Well, how do we solve a linear equation? Well, we want to solve this for t as a function of v, so that's equal to the negative of the coefficient in that equation of the variable raised to the power 0, and then divided by the coefficient of the equation in the equation of the variable to power raised power 1, and then a minus sign. So this is a general form for the solution of a linear equation, and we can see that that's what it gives here. So that's a tool for solving linear equations. This Mathematica function coefficient expression is a function of some expression, a variable, and a power. And we've also used the Mathematica function simplify, which is one of a number of Mathematica functions for factorizing, cancelling common factors, and other high-risk tasks for students. We can see that this is the same as the result of applying the built-in Mathematica function solve using this. And apart from an extra set of brackets, we can see that that's exactly the same as what our tool up here gave us. And we can remove that extra set of brackets using this command. And we can see that this is actually is a solution of the equation by substituting our solution back in and seeing that the result is 0. So it is a solution. We can evaluate the time when the velocity is 0 for the current values of the parameter. We can calculate that using this. So it's a bit more than 2 seconds. Okay, so now let's go on and look at quadratic equations. Well, the height z of t of the particle is we show is given by this formula, and we can see that this involves not just t, it's not linear, but t squared. So this is a quadratic function, and we can establish that using this. Okay, so this quad fun is now a quadratic function of t, and we can establish values of the parameters using our original values for setting v0 and g, and let's suppose that we project the particle from a position 10 meters above the ground. So if we apply those assignments, then this is what our quadratic function looks like, and we can plot that using this, and we're going to plot it from -2 to 5, and I'll explain why that is when we've plotted it. So we can do that, and we can see that the vertical position of the particle, it starts off at 10 here, and we can see that at some previous time it's 0, and the position of the particle goes up and then starts to come down, and eventually comes back down to the ground out here somewhere. And we can see that the graph of this function is a parabola. And what we'd like to do is to find the values of t where the height of the particle above the ground is 0. This basically involves solving the quadratic equation. Well, the way we solve a quadratic equation is we make a linear transformation from t to a variable x plus some parameter alpha. This is a very common strategy in mathematics, and of course it's up to us to choose the value of alpha in such a way that our problem is as simple as possible. So let's apply that transformation to our quadratic function to obtain a quadratic function in the new variable x. And this function collect basically arranges the result as which will also be a quadratic function, but now of x, as something times x squared, and then some constants, and then something times x. Well, we notice that the coefficient of x is a linear function of alpha, and we can extract that by using this. And the obvious choice for alpha is so that this is 0, and that again is a linear equation, and we can customize our tool for solving or finding the solution of that to give this, and so we put that back into this value of alpha, back into our quadratic function, and we get this, and we can see that we've now got a quadratic function which is a function of x squared, and there's a constant term, but there's no term in x because we chose an alpha, so there isn't one. Well, this is actually a linear equation in x squared, so we can solve this for x squared using adapting our tool for solving linear equations. So it's the coefficient of x to the power 0 in this, divided by the coefficient of x to the power 2, and we can execute that, and that tells us what x squared is. Our further progress, which I've omitted here, requires introducing the square root as an inverse function and its numerical calculation using the Newton-Raphson algorithm, and showing that to be the same as the Mathematica function square root of p for non-negative values of p. The generalization to negative values and complex numbers is deferred to the treatment of the trigonometric functions, where the need for complex numbers first arises. Anyway, the solution, assuming that we have that function, the solution, there are two solutions, the positive solution and the negative solution, and we want to simplify that on the condition that g is greater than 0. So let's do that, or according to the condition, and that gives us the values of x. Why have we done that? Well, as we'll find later on, when we discover complex variables, then Mathematica treats all variables as complex. And so that's why we've included this condition here. So we can now find the value or the solutions for t by taking the transformation and then applying the solutions to that and then simplifying the whole lot. And we do that, and we can see that these are these give the values of t, and we might apply the function solve to this function and solve it using that, and we can see that that these solutions are the same, except the orders have been swapped and there's an extra set of brackets. So the numerical values of the zeros can be obtained using this, and you can see there's a positive value, which is when the particle goes up and comes back to Earth, and then there's a negative value, which is the value of the previous time, such that the particle was at height 0. Well, let's think a bit about what we've done here. And in fact, what we've done, apart from generating graphics, is that we've combined three basic operations, which are defining a function, extracting the coefficient of some power or some pattern of symbols in an expression, and replacing a symbol in an expression by some other combination of symbols or numbers, and from which we've built composite tools for solving linear and quadratic equations. And from the example, we see that these tools are repeatedly customized and reused. And the tools developed here can be organized and stored in the student's own electronic toolbox for later retrieval. In this way, we can see that mathematical knowledge is hierarchical. In fact, in all the material I've produced, all operations can be expressed as combinations of these three, which is kind of a bit weird. So let's move on to the next to last bit, which is an analysis of the costs, benefits and barriers. So let me start with the economic model of education, or of university education. Well, first of all, freshman mathematics instruction is big business. For example, it's taken each year by over 2,000 students at the University of New South Wales alone. The next point I'd like to make is that when someone, i.e. students, taxpayers, or a combination, purchases a quantum of education, they're not paying for the knowledge transfer, but the accreditation that some transfer has taken place. Well, this means that universities can make their lectures freely available on places like YouTube without fear of loss, because they hold the monopoly on the evaluation process. Let's look at the costs and benefits associated with the lectures, tutorials and evaluation. Well, the cost of moving to online lectures is initially high, but with recurrence loss costs much lower than the traditional teaching. Other benefits are the freeing up of space in large lecture halls for more productive purposes. The higher the quality of this material, the more attractive that university will be to students and the greater their income. And downloadable lectures have the advantage that students can take them at times that suit them and that the sections can be rewound and viewed again. Note that many fewer teachers would be involved in the delivery of lectures. And I've allowed enrolled students to download my notebooks from the learning management system so that they can execute the narrative themselves, add examples of their own, and cut and paste tools into their project reports. External students taking the lectures online could also purchase the notebooks for a small fee. Well, computer algebra system integrated learning material is essentially software, which very few mathematics teachers are qualified to build. I'm a bit of an exception since I've been involved in numerical computation, software engineering, and artificial intelligence research. So let's go down to tutorials. In tutorials, students work on their current project getting advice from a tutor. I found tutors for my courses amongst the most gifted students who had taken the course previously. A significant effort is involved in constructing good projects whose aims and objectives must be clearly defined and an unambiguous roadmap constructed for their solution. Because they are part of the evaluation projects, projects are downloaded from the learning management system by enrolled students, and teachers can earn brownie points by constructing projects. Each active student submits a project report in the form of a Mathematica notebook, which is executed and initially graded by the tutor to check its correctness. Students taking the course online can participate in tutorials using Skype, using its screen sharing facility. This is where two users connected to Skype can see one of their screen pictures, and of course they can communicate by sound. So let's go on to examinations. Anyway, deep down, most teachers would admit that the main reason for holding written examinations is that they are cheap in terms of teachers' time. I don't know if there are any statistics as to how many resources are used in setting and grading written examinations. Most time is spent on analysing the errors in the scripts of weaker students to try to identify how much they actually understood. Oral examinations are much more widely used in continental Europe than in the English-speaking world. In Denmark, they are carried out by the teacher and an external examiner from another university. The oral examination takes 20 minutes per student, which represents a large increase in the effective face-to-face contact with their teacher. Moreover, since the examination involves the students using their toolbox on a computer, their examination can be recorded, thus further improving the feedback on their performance. A student's final grade is their score in the oral examination multiplied by their total score in their project. So, in other words, you have to pass both elements. Now, students taking the course online can take the oral examination using Skype in the presence of an approved external examiner. This would be a major effort for teachers, with the advantage for them that it would be concentrated in a couple of months of the year. So, well, that's basically the end of the story. Let me just finish by listing a couple of technologies that we So here they are. The first one is Mathematica, which you can learn about from Wolfram. It's a computer algebra system combining symbolic, numerical and graphical computing within a high-quality mathematical text processing environment. The other technology I use is Camtasia, which is available from this place here, techsmith.com. It's a high-quality screen and audio software capture program with video editing facilities, and it was used to produce this talk. And finally, the Skype. It has the ability for this screen sharing, and it enables two Skype users to discuss a shared screen picture in real time at no cost, which is always good. And then finally, YouTube, which is a site where anyone can upload or download a video. Well, that's about the end of the story, so I'll finish here.